All right, so let's take a look at section 8.4. Okay, we started to talk about similarity yesterday. Today, as I said, we're going to focus in on one shape. Okay, just triangles. Okay, keep in mind some of the properties that you know, though. For example, like parallel lines cut by a transversal, alternate interior angles being the same. Some of those properties are going to start to come back. All right, you'll see when we sketch some pictures how they come up. All right, so here's our first example. We're just going to jump right in with an example. Okay, it says in that diagram, triangle BTW, okay, that's the big one, and triangle ETC are similar. Okay, are similar. Okay, what do we know right away? Two things we know. If those triangles are similar, we know that, first thing.
Angles.
Yep, all the corresponding angles are what?
Congruent.
We know corresponding angles are congruent. One other thing that we know. If they're similar, that means the triangles are, they're proportional. Okay, they're proportional. Okay, so let's start with a statement of proportionality. Okay, remember my hint. If they ask you for a statement of proportionality, that's where you write a giant proportion. Okay. For this proportionality statement, how many fractions will there be? 3 fractions. Okay, you need a fraction for each pair of corresponding sides. Right, we can set up the first one, we get a little bit of freedom how we set it up, but then after that, we got to set up the other fractions in the same way. Can anybody fill in that first fraction? And you can almost kind of go back to the problem question, and that will kind of help a little bit. Yep? So this is going to be all letters. So instead of putting in the actual numbers, just give me the letters.
Over EC.
Good. Okay, so Ian did BW over EC. Right? So that's the first one. So now for the other 2 fractions, all the letters from the top need to be from the first triangle, the bigger one, BTW. All the letters in the bottom come from the second triangle. So we've got BW over EC. Okay, so we got those 2. What else? Yep.
ET to ET.
So we got BT, that's the one on the left. ET, that's also the one on the left for the small one. And one more. Yep.
WT over CT.
Let's see, WT.
Oh yeah, WT, my bad. Over CT.
Over CT. That's the one on the big one on the right compared to the small one on the right. Yep, that's a statement of proportionality. Now, Ian had started to plug some numbers in. If you plug numbers into each one of these fractions and did the division, we don't know what the numbers are. Let's pretend we don't know. But we know that each one of the numbers in each fraction would come out what? They come out positive, and if you compared them to each other, they'd all be the same. Okay, they'd all be the same. Right? Because what you're basically doing is finding the scale factor. Okay, maybe we'll do that in one of the parts later on. If not, we'll come back to this and we'll figure out what's the scale factor. Okay, next, find the measure of angle TEC. Okay, so remember what Connor told us, all the angles are congruent. So if you know the angle that corresponds to TEC in the big triangle, you got your answer right there. Okay, so Connor, what's the measure of angle TEC?
79.
79. Okay. TEC and TBW. Those are corresponding angles. Okay, so they're both 79. And last part, find ET and BE. Start with ET. Okay. Now, keep in mind, we have proportions already set up. We can use these. Let's start with a proportion that has some numbers in it we can fill in. Okay. Is there any proportion there that we can fill in some of the numbers? Jacob? Start going through. Do you know BW?
Yes.
Yep. Do you know EC?
Yes.
Okay, let's fill in the numbers in that proportion. What's BW?
12.
12, and then EC? 3. So let's fill in, okay, 12 over 3.
4.
Okay, so we'll put the answer up here in a second. All right, so we got 12 over 3. Now look for the fraction that has the ET in it, the one in the middle. Okay, do we know BT?
20.
Yeah, BT is 20. How about ET?
No, we don't know yet.
Right, that's the side we don't know.
It can be figured out.
Okay, so all I did was take these first two fractions, okay, filled in the 3 numbers that I knew, just looking at the diagram. I'm going to find the one number I don't know. All right, so we're going to cross multiply. 3 times 20 gives me 60. 12 times ET. Just write it as 12 times ET.
Isn't there an easier way to do it?
And what's my last step?
60 divided by 12 equals ET.
Divided by 12. Okay, so how long is ET? We divide each side by 12, and we get ET is 5. Okay? Any question on ET? Okay, now that we know that, we could use it to find something else, or just go back to the 3 pieces of information that were given. Okay? Now we want BE. Okay? Well, BE we don't have to set up a proportion for. Because is BE part of a triangle? No. BE, if we take the side that's 20 units and use that, and somehow use what we just found, what can we do with those 2 numbers to find BE? Yeah, subtract them. If you take BT and subtract out ET, you'll be left with what we want. All right, so take BT, subtract away ET, and that'll leave you with this piece, BE. Okay, BT, let's go back up. We already know that. Okay, BT, 20. Okay. ET, just found it in the last problem. So we got 20, ET's 5. How long is BE? 15. Okay, there's all kinds of ways to think this through in your head. What I'm trying to do is show people a very mechanical, mathematical way to do it. If you look at it and you're stuck and you have no idea what to do, this will hopefully give you a process to follow. But the idea is set up a proportion somehow if you're trying to do it mathematically, basically for every problem today.
So there is another way of doing that?
Yeah, there's different ways you could set up this proportion, absolutely.
Well, I wouldn't even cross multiply there.
Yeah, I mean, there's all kinds of ways you could solve it. All right. What's the scale factor between these 2 triangles? Yeah, if you compare the big one to the small one, it's 4 to 1. Okay, the big one is 4 times bigger. All right, so I think we finished everything there. All right, so the next thing we're going to look at is a shortcut for how you can tell 2 triangles are similar. Okay, by the definition, you got to compare all the angles, make sure those are the same. Then you got to compare all the sides, make sure they're proportional. While with triangles, there's a shortcut. Okay? if you have a triangle and two angles in one triangle are congruent to two angles in another, then the triangles are automatically similar. You don't even need to compare the sides. Now, this idea doesn't work for shapes like quadrilaterals. Because I could name you two quadrilaterals, all the angles are the same, but they're not similar. Think of a rectangle and a square. All the angles are the same, but they're not similar. But in a triangle, if all the angles are the same, or all the angles are congruent, corresponding ones, they're automatically similar. Now, how come you only need two? It says if two angles in one triangle are congruent to two angles in another. What about that third angle? Denver?
Because two angles determine the third angle.
Right, the two angles determine the third one. Because there's only three. They all have to add up to 180. So if you know two of them the same, the third one has to be the same. Okay? So here's a diagram of that postulate. Okay. I'm saying angle J and X are congruent. K and Y are congruent. These are similar. And I think this one gets kind of the point Owen had mentioned earlier. Can you take and you turn it? Or if you reflect it, that's fine. This one looks like it's been turned a little bit. It's smaller and it's been turned. But it is still similar. Okay? What is this called? Triangle JKL is similar to triangle XYZ. If I wanted you to write something like this on the test, what would I ask you for? I'd ask you to write a what? Yep. The statement of proportionality is when you have that giant fractions. Okay, think of statement of proportionality. Think proportionality is a proportion. All those fractions together. But it's a good guess. This is something, I think we mentioned them at the same time yesterday. This is a similarity statement. Okay? The way you know that, look at the symbol. This is the similarity symbol. It's called a similarity statement. All right? All right, so let's look at this one. Okay, in those two triangles below, each of the vertex angles is 52 degrees. I want to know why these triangles are similar. Okay, well, what kind of triangles are they, first of all? Okay. Yep, they are isosceles, because you got two sides marked the same. Okay, we know that's 52. And that's 52. What makes them similar? Let's focus on that big triangle. What if I asked you to find the two angles at the bottom? How would you do it? Connor?
52 minus 180. Then divide that by 2.
52 minus 180?
180 to minus 50.
Gotcha.
There you go, Connor.
And then why divide by 2?
Because it's two angles that are missing.
But dividing by 2 assumes they're equal.
Scaling. Scaling triangle. Two angles.
Okay, if it's scalene, then that means we should have 3 different angles.
No, not scaling.
Yeah.
Isosceles.
Yeah, it's isosceles. Okay, so what Luke said originally, these two sides are the same. The two angles across from those sides have to be the same. So that's why you take what you have left, divide by 2, and then each one is 64 here and 64 there. Well, if you do the same thing in the smaller triangle, these two angles at the bottom also have to be the same because it's isosceles. You'd go through the exact same calculations. That's 64. And that's 64. So what reason could we give why those triangles are similar? We just mentioned it. Yep. Yeah.
Did you just do angle, side angle?
The angle similarity postulate.
So, Mr. Hager, when any isosceles triangle that share the same one same angle, and that automatically makes them congruent? Or not congruent, similar?
Similar, yeah. Because an isosceles triangle, if you know these vertex angles are the same, it's automatically what we just
You
had.
don't even know the vertex angles are the same. You could know one of those angles in the corner.
Yeah, if you knew the base angle, well, that's 64. The other one has to be 64, and then the other one has to be 52. So as long as you know one of the angles in an isosceles triangle is the same as another angle, then yes. Now, would that be true for any triangle? If you just know one angle? No. Okay. You could draw a triangle that's like that with a 90, and you could do one more like that. We do have one angle that matches, okay, but they're not isosceles, so you don't get that other angle. All right. So bottom line, in a triangle, you got to have two angles that match, and then they're similar. All right, let's look at this. Okay, so this picture, there's a blimp. Okay, there's a camera mounted to the bottom of it. Okay, it's taking a picture. Okay, and if you want to know what some of this stands for, okay, H is the altitude of the camera off the ground. Okay, G is basically how wide of an area on the ground that the camera lens can see. Okay, because camera lenses can only photograph so wide of an image. Okay, N, I believe that's the distance across the back of the camera. And then F is a measurement from the front of the lens to the back of the camera. Okay? You don't need to know all the specifics there. Okay? They tell us that we can use this proportion to estimate the altitude. Okay? So you can use this proportion to estimate the altitude. Okay? And that, hopefully if they're, making up a real problem in our book, that should really work. Okay? If you could measure a couple measurements on the camera and then measure, the distance on the ground in a photo, you could estimate how high up the camera was when it took the picture. Okay? It should actually work. Right? So they give us some numbers. They tell us that F is 8 centimeters. Okay. N, distance across the back, is 3. And the distance on the ground, okay, how wide of a picture the camera could take, was about 5,000 centimeters. Okay, so if we fill that in, we should be able to figure out how high was the camera when the picture was taken. I wouldn't expect you on a test to be able to come up with this on your own. I would give you the formula.
Thank you.
All you have to do is fill in the numbers. Okay, so let's do it. What's F? Kiara? Yep. F is 8. Over Sarah? What's H? Help her out?
I just have a question. Is 8, are we trying to figure out how tall the how far away is the camera from the blimp?
From the lens of the camera to the ground.
From the lens to the ground.
So we don't know H.
Exactly. We don't know H. Okay? We don't know H. How about N? The distance across the back of the camera. Yep, Selena? 3. And lastly, G. We're looking at the picture now, and maybe somehow we're looking at the picture and we can figure out how wide of an area it is. Maybe it's to scale. There's like a scale on it. We can figure that out. It's 5,000 centimeters. Okay, is that a lot? 5,000 centimeters?
No.
Well, if you changed it to inches, there's about 2.5 centimeters, 2.54 centimeters in an inch. Okay, so if you took the 5,000, divide by 2.54, it's about a couple thousand inches on the ground. So if you divide by 12, It's an area that's about 164 feet across. It's a good size. It's like half a, a little more than half a football field. Football field is 100 yards, so it's 300 feet. So think of it from like midfield all the way to the end zone. It's a good size area. It's not huge. Certainly not high enough to be taking pictures of like an entire city. But maybe they're taking a picture of like somebody's property because they're gonna like Google Earth. They do that. They get the satellite imagery, different levels. Something like that. Okay, so what's the technique called we use to solve a proportion? Cross multiply. Who can tell me what I get when I cross multiply?
H3.
Yep. And what's 5,000 times 8? Well, start with, I was going to say start with 8 times 5, which is,
45.
what's 8 times 5?
40. I'll do 9.
And now add on the zeros. So 8 times 5 is 40. Add on 3 zeros, 40,000.
That's too much money for my page.
Divided by 3. So our height, okay, remember this is in centimeters. Okay, our height is 40,000.
16.
Divided by 3. So it's 13,333. Okay, if we divide, in this part, you don't have to know this conversion, but if you divide by 2.54, roughly, that's how many inches this camera is off the ground. Or roughly in feet. So it's pretty high. I mean, it's about 437 feet off the ground.
How many meters? Because it's a metric.
I converted it using 2.54. It's a weird conversion, but if I just happen to know there's 2.54 centimeters per inch. Yep.
No, convert it to metric.
What's that?
Then you gotta convert it to metric.
Yeah, I didn't want metric because I have an easier time visualizing it in feet. Okay, but if you can visualize something in metric, that's fine. That's probably how the book is going to leave the answer. What they might do is change it to meters. How would you change 13,333 centimeters to meters?
We don't do that.
You should know how to change centimeters to meters because the conversions are very easy. It's all powers of 10. Yeah. Yeah, you divide it by 100. Okay? So if you divide it by 100, you get 133 meters. Okay? Well, if you want to convert to kilometers, well, that's 1,000, factor of 1,000. Yeah.
You know all the metric prefixes?
Yeah.
I know
All right. Let's see in the book. In the book, they did write it as meters. Okay. So if you see the answer in the book, they wrote it as 133 meters. Okay. I'd accept that. I don't expect you to convert. All right. All right, so last thing. In 8.3, okay, we learned that if you can figure out the scale factor between corresponding sides, that scale factor also works for the perimeters. Okay? So if you've got two shapes and one side is twice as big than the other, well, then the perimeter of the bigger shape is twice as big than the perimeter of the smaller shape. Okay? The perimeters are in the same ratio as the sides. Well, we can extend that idea to basically any corresponding lengths, okay, in triangles. It doesn't have to just be the sides. Okay? If the sides are in a ratio of 2 to 1, the altitudes are in a ratio of 2 to 1. The medians are in a ratio of 2 to 1. Okay? All those special segments we talked about, altitudes, medians, segment bisectors, angle bisectors, all that stuff. They're all proportional, okay, to the scale factor. Does everyone see that idea? So when you make a larger version of a triangle, you make everything larger. You make the sides larger. You make, except the angles. The angles stay the same, but you make the sides larger. You make the perimeter larger. You make the altitudes larger. You make the medians larger. Everything is increased proportionally, exactly the same amount. Okay? So we're going to use that idea to try to solve our last problem. Okay. Does everybody have up to if two polygons are similar? Try to scroll up a little bit. Okay, so in this problem, something's going to come up that I said at the beginning of class to keep in mind. Some things are going to start to come back. Okay, so we've got two triangles. I want to find the length of QS. Okay, QS is an altitude. Okay, any line that comes from a vertex perpendicular to the opposite side, that's the height of the triangle. Now, I know something about the height of this other triangle above it. It's 6. But that doesn't help me unless I know these triangles are similar. If they're not similar, we're going to have a hard time solving it. But if we can show that they are similar, we can use the idea up above. This can be very easy. So the first thing I need to know is, are these triangles similar? And if so, how can I prove that? If we're going to use angle-angle similarity, prove to me why there's two angles in each triangle that will match. Connor?
The right angles?
Think of the big triangle, yeah. So
We don't know any
NQP
of those yet.
and RQT.
We don't know any of those.
Well, we're just trying to show if they are similar. Do we have enough information?
Yes.
Okay.
You know, 16 and 24. Tops.
To show triangles are similar, what's the name of that theorem? Or postulate, sorry, it's a postulate. Angle, what? Angle postulate. So you want to focus on angles. Okay, if you're trying to show these are similar, somehow we have to prove we have two angles the same. One of the angles is a very, very basic theorem we talked about early on about lines that make an X shape.
I know.
Yep.
Vertical angles.
Yeah. By vertical angles, we have those two the same. Okay, so that's one, but we need one more. This one's a little trickier. So somehow we're looking at angles N, P, R, and T. Is there any way that I can show those are the same somehow? Pick one of the angles in the top is the same as one in the bottom.
Alternate interior angle.
Okay, what about alternate interior angles?
They're the same, brah.
They're the same if what?
If they're on a parallel line.
Right. Okay, this little tiny mark here, very important. As Luke noticed, we have parallel lines. Well, if you've got parallel lines and you cut them by a transversal, alternate interior angles are equal. Perfect. So now, these triangles are similar. Okay? We've proven they're similar. All right. What could I set up for a proportion? Or if you're not sure what to set up, maybe just try to find that first. Try to find the scale factor. And then if you can find out the scale factor between the two triangles, and we know the height of one of them, then we can easily find the height of the other one. But let's get the scale factor first. And let's do it from the big to the small. So big over small. Okay.
Scale factor is 3 to 2.
Okay, can you explain how you got 3 to 2?
As I took the 6 and I said 12 over 6 equals 8 over x instead of that.
All right, so for scale factor, you're just going to compare two numbers. Like you said, the 3 to 2. How'd you get 3 over 2? Because there's no x in that, right? 3 and 2. So for now, just leave the leave the variable out. But I understand where you're going with it. But how'd you get 3 and 2? Because I don't see 3 and 2 up here.
Just I took put it over 8.
Yeah, he compared corresponding sides. Okay. Another way you might do it is compare the length of NP to the length of RT. Those are corresponding sides in the similar triangle. NP is 24. RT is 16. And if you reduce it, 8 goes into each one of them. 8 goes into 24 3 times. Goes into 16 twice. Okay. So there's our scale factor. All right, so now let's extend that a little bit. Okay, I already know this. I'm going to fill in 3 over 2 in a second. What other two sides do I need to compare to find QS? QS is one of them. What's the key side you need to look at in the top triangle? Oh, Olivia? What side corresponds to QS?
MQ.
Yeah, MQ. I'm going to start with, since I started in the middle and went towards the bottom, I'll start at the middle and go towards the base of it. Okay, so I'll call it QM. But that's perfect. Okay, so QM is the height of the top. QS is the height of the bottom. We know this. We know that. And we know that. Find QS. So NP over RT. Let's do the reduced form. That'll be easier. 3 over 2. QM. Connor, how long is QM?
6.
6 over, you could put X or you could just call it segment QS. Okay. You know what? Since I'm actually finding the length of it, I'm just going to put QS. Okay. Right, so cross multiply. 6 times 2 is 12. 3 times QS. So how long is QS? 4. Okay, did anybody see another way you could just look at this fraction and solve it? There might be even the other ways, but I just want to look at this fraction and solve it without cross multiplying. This one you can kind of do with a little trick because of the numbers. Yep.
How many times 3 is that? 3 times 2 equals 6. So
Right.
2 times 2 has to equal 4.
Right. If you multiplied the top by 2 to get 6, you have to multiply the bottom by 2 to get an answer of 4. Okay? That's another way you can solve it. This works if you don't have fractions or decimals or messy numbers. Okay? But if you have a number like this, 3 over 5 equals 13 over x, well now it's not quite as easy because you don't multiply 3 by an integer to get 13. Okay? Be a little messy. You could still do it that way. But if you get stuck, just go back to your cross multiplying. Okay, so any question on that idea? If you scale up the sides, you scale up everything. The altitudes, the medians, every special segment in the triangle. Okay there. All right. So, put up. Okay, so the homework. Again, the homework, you got 3 days to do it. You got Tuesday, Wednesday, and Thursday night. I'm going to check it Friday. It's Friday 27th. All right, so 483, 10 to 16 even, 18 to 21 all, 23, 28, 33 to 38, and 40 to 48. just evens on 40, 48.